Good afternoon, everyone, and thank you so much for inviting me, and thank you for that kind introduction. It's great to be virtually back at Texas A&M. So today I'm going to talk about local Gaussian process regression. And before I get started, I think I should give a brief history about this work. So I started working on local Gaussian processes when I was on the faculty of Oklahoma State University with my PhD student, Bob Akfarmanish, who is currently a data scientist at Dell Computers in Austin, Texas. After I joined Google, I decided to continue working on this topic, first because I was interested in developing a Python package for visualizing spatial data. And second, I was interested in improving the theoretical results that we developed. I realized that those results could be improved. And having said that, I should emphasize that this talk is primarily theoretical in the sense that I'm going to talk about mostly challenges in local Gaussian process regression with a focus on developing error bounds and utilizing that. At the end of the talk, I will also point to a few resources, my prior works and other works that deal with the application of such methods in real data. And I have a total of 22 slides, and this is the brief overview of my talk. So I'm going to start with an overview of Gaussian process regression. I'm not gonna spend a lot of time because I assume most people at least have a basic understanding of Gaussian process regression because that's a popular topic in machine learning, and many people I assume in the audience know a lot about Gaussian processes. And to my knowledge, there was a tutorial by Rui a few weeks ago. So hopefully for those who had not been familiar with the GP, hopefully they were all able to attend. Nevertheless, I think it's a good idea to spend a few minutes just to emphasize the points that we need from Gaussian processes and set up the notation. Then, as the title of the talk suggests, I'm going to focus on local approximation. So local here, on a very intuitive level, means you, instead of fitting a global model everywhere, you look at smaller regions. And I talk about the most important aspect of that local approximation, which is creating subdomains. And at the end of the talk, I will also, as I mentioned, talk a little bit about some practical considerations. Okay, so let's get started with just a brief overview of Gaussian process regression, just a review to see what we are interested in here. So the setting that we are looking at is as follows. We are going to predict quantity based on a limited number of observations. So this is, as you know, is a very general setting that includes all regression problems. So we need to narrow our focus. The first is that we are dealing with quantities that are spatially varying. So you can think of spatial data. So you can think of, we have features such as latitude and longitude, and then we want to predict, let's say, temperature based on observations of temperature and some scatter points. Some of the results that we have here can be applied to general machine learning problems, but generally we are dealing with problems in spatial data, and the features could include exogenous variables. So it could be latitude, longitude, temperature, pressure, and other things. The scope of the problem is still very broad, so we need to further narrow it down. The space of functions that we are going to look at is as follows. We want to have the predictor to be a linear combination of observations. So this is different from a linear model. In machine learning, this is called a linear smoother. That means what you predict is a linear combination of other observations, not necessarily of your features. So for example, on the right-hand side here, you see just a few black points. So we assume that these black dots that we have are realization of some underlying stochastic process. That's another assumption that we're making. And at the location that we don't have observation, we want to make a prediction, that red star dot. So we assume you observe a random field denoted by the vector capital F at n locations. Those x1, x2 are inputs. Think of them as spatial locations. And you want to predict that f of x star, the problem that you mentioned. I assume that's temperature at that point. So one natural way to do that is to minimize the expected error, 0.3 here. So this expectation is with respect to the underlying stochastic process. So we have a stochastic process. We know that f of x star is a random variable, and all those f's are random variables. And then we want to see how we can, on average, reduce the squared error and what would be that c. So it's easy to see after a little bit of computation that if you take the derivative and set it to 0, the optimal vector that gives you the linear combination is this matrix. So that this matrix times this vector. So that the first matrix is the covariance matrix of all your, say, training data, and the second vector is the covariance vector between that test point x star and all the other points. So this one gives you your best linear predictor, because best in the sense that it minimizes mean squared error. Now, so far I haven't talked about the Gaussian distribution, but if you also make this assumption that the data, that is those observations, are normally distributed, not only any one of those, but any finite combinations that you have, they are all distributed according to a Gaussian distribution, then it's easy to show that the conditional distribution of the quantity of interest, given all the other observations, is a normal distribution. And this, the first vector here is just the transpose of that C. So it's a linear combination of all those variables. And the second term is the conditional variance. And let's emphasize a few points here before we proceed. The first one is this mean zero assumption. Is it a very strong assumption? In general, no, because even if we assume a mean zero prior, the posterior is not necessarily mean zero, as you see here in the stochastic process. However, you can think of problems that you have an explicit formula for the mean, and then whatever is not explained by the mean function, you can assume that's a Gaussian process. That's called universal kriging, as opposed to simple kriging that we're doing here. You can refer to some of the texts about if it's a good idea to use a general mean function, like the book by Stein, a simple theory, some theory for kriging. But in general, let's assume that we are going to use a mean zero prior, and then if there is a constant mean that we know, we can just subtract that. The second point I need to emphasize is this matrix K. So K is an n by n matrix, and we use a function that is of two variables at those indices. So this is called a kernel in the theory of integral operators or numerical analysis. And that kernel gives us the expected value of these two, the function multiplication, which is the covariance function in here. And we will get back to this kernel later in the talk. But the important thing about this kernel is that first, this must be positive definite. That is the integral of this k times f times another f over all xi and xj's should be positive. The second important point is, if you fix one of these x, let's say fix xi, and think of this as a function of xj, that will lie in the same space as the function f. I'll get back to this point later. And this second one is also, you can think of it as the function of x star that shows the correlation between the covariance, in fact, between your test point and all the other points. So you see there are similarities between this and kernel regression. The difference is that in kernel regression, you just look at this normalized kernel. In Gaussian processes, you look at not only the kernel itself, but the covariance between all those points that we have there. And you can think of equivalent kernels, like can you find another kernel that's similar to this multiplication and so on. And the final point is this term conditional variance or predictive variance. So keep that in mind. We'll get back to this point later because this is an important quantity. So this consists of 2 points. We have the prior variance, and this is the information that we gain. This is a quadratic form. So this is the variance reduction that we have. Okay, so this is practically all we need for Gaussian processes in this talk. I just wanted to emphasize a few more points here. The first is that if you look at that mean function as a function of x star, that has a relation with what is called in the numerical analysis radial basis interpolation. First, it's easy to see why that interpolates because if you insert one of those xi's as x star, then this will be orthogonal to all the columns here, and then will return 1, so you can recover your point. Now the question is it reasonable to assume interpolation? In some settings, yes, like visualization, computer experiments. But the good news is you don't have to make that assumption. You can assume additive noise, and then this matrix here will be k plus a diagonal term. Then in that case, your predictor will not interpolate points necessarily. It will go above and beyond, below them. But here, just we can assume that we are dealing with an interpolator. Another reason I mentioned this radial basis interpolation is that there are a lot of powerful mathematical tools from numerical analysis that we can use, but we need to emphasize that our setting is a little bit different. Here we are assuming we're dealing with stochastic processes. In numerical analysis, generally the assumption is we are dealing with deterministic functions. So some of the formulas are identical. Some of the way we interpret things could be a little bit different, especially when it comes to uncertainty quantification. For example, that predictive variance, that can be also achieved using tools in numerical analysis, such as power functions. But the way we understand that as a variance of a process is different. Just wanted to make this emphasis here as well, though we will use many of the tools in numerical analysis. Another point we need to make is that the importance of the covariance function. As you see on the right-hand side, we can use 2 different Gaussian processes to interpolate the same number of data points. So the blue points are identical, but the 2 Gaussian processes are different. And the difference here is the difference between the covariance functions. So for example, the one on top is a covariance function that if points are far away from each other, like in this region, assumes there is no correlation. The one on the bottom is a smoother, assumes there is a large correlation between points. And there are different classes of covariance functions that you can use, but the point here is the covariance function that you use determines the behavior of the process. And another point that I will get back to at the end of the talk is that we can think of a true covariance function that the underlying Gaussian process uses to generate the data, but we can just use a specified covariance function, and we want to see what happens. So GP regression is a popular tool, simply for many reasons, but 2 I wanted to focus on here is one, the closed form solution. So as you saw, what we have as the predictor, predictive mean and variance, they have a closed form solution. So if you start from a statistical decision theory perspective and see, and you want to minimize the loss function, it's not easy because that includes interactable integrals. But if you assume the Gaussian distribution, you can analytically calculate those integrals. The second one is theoretical properties. So there are, we do have a set of nice theoretical properties that at the end of the talk, I will share a few references, for example, about uniform bounds, consistency, convergence rate, and among other things. If you think of this function, the mean function, as a function of, again, x star, and you see the second term here, k inverse times f, think of this as a vector, then you see that this one is a linear combination of kernels evaluated at n training points. And this interpolator has the lowest Hilbert norm in that space for among all the other interpolators. Okay, so now the one problem with Gaussian process is that it's computationally inefficient in the sense that it's of order of n cubed. First, n cubed is polynomial, so it's good in general when you compare it to many other algorithms that are, they have much worse computational complexity. But in many practical settings, even n cubed is computationally intractable. And I should also mention that when we say it's n cubed, that means the largest computational cost. We can think of storage, initialization, mean prediction, and variance prediction. For example, once you do initialization, the mean prediction is of order of n, and variance is of n squared. But I'm talking here overall, if we consider everything is n cubed. So this encourages us to consider approximation techniques. And I'm going to spend a few minutes talking about a few of those approximation techniques. The first one is using a compact covariance function. So a compact covariance function means that covariance function, that kernel that we talked about, it has an image that is closed and bounded, and it's zero. It's literal zero outside a set. Now, when we have a compact covariance function, the covariance matrix will be sparse, obviously, because we will have a lot of zeros. So now here the question is, K inverse is not necessarily a sparse. But from numerical analysis, I know most people know here that when we have a matrix multiplication of K inverse times F, we don't need to calculate K inverse and multiply it by F. We can think of this as the solution of the problem K times some unknown vector is F. So we can use, say, conjugate gradient techniques and go up to a certain step. And if we have a compact covariance function, that K is sparse, and then if we use techniques like conjugate gradient, that we can approximate it very fast. The second one is likelihood approximation. So because we are dealing with a Gaussian process, so it has a normal likelihood, then you can think of how I can use another likelihood, for example, to conditional on it, or just use a subset of data to define different likelihood and do conditional inference and so on. And those are like all powerful tools. And there are like many other methods, but I just wanted to get to local Gaussian process regression. So local here means, let's say again, in a one-dimensional case, instead of fitting a Gaussian process to the whole set, we can, let's say, create 3 segments here and say, oh, we ignore for the segment that is under the green line, we ignore everything else that's outside, and then we fit the Gaussian process here. And for the blue line, again, the same. And for the red region, we do the same. So obviously there are 2 questions here. One is how to create those segments in one-dimensional and in general regions in multidimensional cases. And as you see here, we are dealing with discontinuity. So how to deal with those? So these are 2 big questions about local Gaussian process regression. Let's talk a little bit about this local Gaussian process, and we'll get to these 2 points in a minute. So first, now imagine on the right-hand side, you have n points. So here we are looking at a 2-dimensional case, and so so let's assume the vertical axis is longitude and the horizontal axis is latitude. And then at those points, we have observed data. And then a local Gaussian process is something like this. You create regions. I just arbitrarily chose some regions. So in this case, the computational complexity will drop to nm squared. So m is the average number of data points that you have in each region. One of the reasons that we are interested in local GPs compared to the other two methods and other approximation techniques in general for spatial data is that we have better, we have an easier time handling heterogeneity in data. That means if you can think of this image on the right-hand side as a region on Earth, then sometimes it's possible to use like sophisticated covariance functions to kind of model different behaviors in different regions. But if you have like a heterogeneous process that behaves differently in, like, say, one of the regions compared to the other one, local GP enables you to use different parameters for each region and so on. So in addition to the computational benefit that we gain from splitting the domain into a smaller subsets. And as I mentioned, the two issues here is first this discontinuity on the boundaries, because if I like use a Gaussian process for this region, what about this boundary here? So we have three different values here. So you can think of, if we have a Gaussian process that predicts temperature, then you create one region for College Station, one region for Bryan, then you have like a discontinuous process because on the boundary of these two cities. And another obvious question is how we should create these subdomains. You can think of an infinite number of ways. And I also wanted to use this slide to just summarize this talk in the last bullet point. So what we propose here is to use parallel hyperplanes for creating subdomains, something like this. So why do I call them hyperplanes? So in 2 dimensions, we can think of parallel lines. In 3 dimensions, there are parallel planes, and in higher dimensions, there are parallel hyperplanes. The reason we propose this approach is because first, it's easier to impose continuity in higher dimensions. And then it's easier to characterize such decomposition, because all we need is just one single normal vector that determines, in fact, the entire decomposition method. Now, one problem with this, based on even this simple plot, you see that doing this may result in very large subdomains, large both in the physical sense and large in the sense that you may have a lot of points. Then even when you create local regions, approximation might be needed. So for that, what we do, we use a reduced rank approximation for the kernel, which I'm going to talk about in detail. And now the good thing is, because we can easily characterize those parallel hyperplanes among all the possible hyperplanes that we have, we choose the one that minimizes an upper bound for the error for that reduced rank approximation. Because we may also have this set of parallel hyperplanes, but now we create an upper bound and then we minimize that, and then we can find hyperplanes that create smaller subdomains that you can use reduced rank approximation with a minimized upper bound. Okay, so and that's like the summary of this talk, and I'm going to talk about these steps in detail. But before that, as I mentioned, there are 2 points. One is creating those hyperplanes and reduced rank approximation. The second one is imposing continuity. I'm just going to spend one slide on imposing continuity. This is an important topic, but not the focus on this talk. Before that, I should also mention that in numerical analysis, you see this discussion about if we need to impose continuity for local methods. In some cases, no. Because when you impose continuity on average, you make things worse. In certain settings, we may need to do that. For example, for visualization is one problem. If you want to create a surrogate model, and that surrogate model has to be continuous and so on. But let's assume we need continuity. And that can be done simply by recalling that the Gaussian process regression was an optimization problem from the first slide. That was an unconstrained optimization. We just found the derivative and set it to 0. Now, for local GP, when you impose continuity, you just need to make it into a constraint optimization. So you say we want to minimize this expected value subject to a set of constraints on the boundaries. There are many different ways you can do that. One way is to create control points. So you look at the boundary and then you find certain control points denoted in red, and then you can say something like I can fit a GP, and then I impose the mean predictions in each region to be identical to those points. And after that, what you get is the mean and variance functions that are the same as those of GP plus certain correction terms. And at the end of the talk, I will introduce a few references I mentioned to here, especially the first one, and a few follow-up papers by the same lead author. But that's the whole idea here. And then you see, once we have parallel hyperplanes, one of the good things is that first, it's easier to impose continuity for one. For each region, we can only look at the region next to it, not all the other regions. Okay, so this was about continuity. Now let's get to our main topic, which is using reduced rank approximation in each region. Before that, we need to review a few things about covariance functions because these are critical for our analysis as we proceed. So I just wanted to remind the audience about a few points that we're going to use. I assume most people are familiar in the audience with reproducing kernel Hilbert space and eigen decomposition and so on. But just a reminder, and just with an emphasis on certain points that we need in this talk. The first one is, remember that we said that covariance matrix is evaluated, the values are based on something that we call a kernel at 2 points. Now, this kernel defines a reproducing kernel Hilbert space. Now, on a very intuitive level, you can think of an RKHS as a set of well-behaved functions. So more on that, when we deal with like approximation theory, we need to narrow the space of functions that we are considering. So one example is like we only consider L1, set of functions that are integrable, that absolute values are integrable. Then the problem is that's not a Hilbert space, so we can look at L2 with a nice geometric structure. Now the problem with L2 space is that convergence in L2 does not necessarily result in pointwise convergence. Which means that L2 also includes a lot of erratic functions. So to get pointwise convergence from convergence in norm, we can think of a Hilbert space for which the evaluation functional, that's the functional that takes a function and gives you the value at a certain point, is bounded from above, hence continuous. And by Riesz representation theorem, that means there is an element in that space that can evaluate every function through an inner product. And that one is this kernel K. So think of it as, again, assume this xj is fixed, and then the first element can vary. So you have a function, and then think of all the linear combination of those functions, and then define a bilinear form, and then complete that in the sense that find this closure, assume every Cauchy sequence is convergent, and that will give you a Hilbert space. And the point I want to emphasize that Hilbert space is unique. So once you give me that K, I can tell you there is only one Hilbert space like with that representer. And if I give you a Hilbert space with a representer, that must be K. Now, the second point that we need is the notion of eigenfunctions. Eigenfunctions are just like eigenvectors. The only difference is instead of a matrix times a vector, we have an integral operator. And another point I wanted to emphasize is that those eigenfunctions and eigenvalues depend on the measure that you use. So the RKHS is unique, but eigenfunctions depend on the measure. And if the space that you have uses a finite measure, like a probability measure, or you are dealing with the Lebesgue measure on a compact set, then you can express that kernel as an eigenexpansion. So this one is just like matrix diagonalization. So just think of this K on the left-hand side as a matrix. Then on the right-hand side, you have lambda I times UI transpose, or conjugate complex. And we don't have this, just like that we don't have this for all the matrices. Here we are pointing out that this is only for finite measures. And finally, though you can analytically calculate eigenfunctions for certain kernels, sometimes we need to approximate those. And that's easy through Monte Carlo approximation of this integral. So if we have m points, and then we evaluate that integral at m points, we get m equations like this. Now, if you evaluate those equations at m points, then you get an eigen problem. So if you have m points, you can find m eigenfunctions at m locations. And you see, for other locations, this equation also gives us how we can interpolate those. So once you have, let's say for phi I at m locations, at other locations will be just the multiplication of this matrix times this vector, or this function, in fact, times this function. And this is all we need. I just wanted to review basic aspects of eigenfunctions, kernel and integral operators, and eigen analysis. So just to summarize, each kernel, you can think of it as a function of two, fix one, then consider only the other one as a variable. Finite combination of those functions, when completed, will define a unique Hilbert space. We can think of the notion of eigenfunctions. We can, for finite measure space, we can think of kernel diagonalization, loosely speaking, and we can approximate those things through eigenproblems. Okay, now, why do we need all these here? Let's get back to our problem. And that's, we need these concepts because of the way we create subdomains. So recall that we use parallel hyperplanes. In the previous slides, I randomly showed some possible cases for parallel hyperplanes. And the reason we need this reduced rank approximation, as I will mention, is because each of these regions could still be huge. Now I'm using like a few points in each region, but assume there are like tens of thousands or hundreds of thousands of points in each region. So even if you use the local approximation, the region, each region is still huge. So let's say we are focusing on only one of these regions. So the idea in local Gaussian processes is that use a full Gaussian process for this region. But for the reasons I mentioned, we need to use a reduced rank approximation because of the way we create subdomains. These regions could be huge. So from now on, assume we are dealing only with one of these regions, but these regions are variable. That is, those red lines can switch. So let's see how it works. So again, looking at this single region, if you look at all the points in that region, this is a schematic representation of the covariance matrix there. So one thing you can do, remember, we can approximate eigenfunctions and eigenvalues using Monte Carlo approximation integration, and then recover that kernel. So we can do this. Look at only a subset of these points. In this case, the 4 points on the top left. And then use these 4 to approximate eigenvalues and eigenfunctions. So see how it works. If you do that, so in each region we have m points. So this is an m by m covariance matrix. But here we only look at p points, which is much smaller than m. And then use these p points and use the integral operator and use Monte Carlo approximation to estimate covariance function. And this is what you get. So instead of using all the m points, I am using only p points. This p in the numerator is just for normalization because of difference of normalization between matrices and functions. And here I can recover this reduced rank kernel not as a finite combination of all the eigen functions at m points, but only at p points. So it's like, remember, so if we have m points, we can estimate m eigen functions at m points. Now we are using only a subset of those. So we can use only a subset of eigenfunctions. Imagine when you have a matrix diagonalized and you have all m vectors, just imagine you are throwing away some of them, and then something like eigenvalue approximation or singular value decomposition, and you get a reduced rank version of that matrix. So this is the same for kernels. Now, if you insert the equation for VIPX using the last equation that I showed on that slide, that at any arbitrary point, you can use it as a multiplication of the kernel times that matrix, then you see that that matrix K P by P will reappear here. And that's the whole idea of reduced rank approximation. So in this case, if you use this kernel, instead of inverting an m by m matrix in each subregion, you only need to invert a p by p matrix. Of course, if you have n points, then that will be, sorry, m points, that will be m p squared, because m is larger than p. But this is a significant reduction in computation. So instead of using all the m points to approximate the kernel, we only use p of those, and then we get a reduced rank approximation like this. So let's see what another question we need to ask here is the error of this approximation. So we know we can approximate it like this, but what is the error? And the error here, there are different ways to define the error. And here I put it like this: the first statement here, the error in the metric induced by the RKHS norm is this value. Probably this requires a little bit of explanation why this is the case. But first, by this, I mean, if you look at this expression here, you see this is a linear combination of the quadratic form, but you can obtain this reduced rank approximation simply by making this assumption that I want to have a kernel that is based on a linear combination of all the other kernel values at fixed p points, and then minimize the RKHS norm, which is a reasonable thing to do, and then find the best value for those linear combinations, and then you will get the same form. And the error of that approximation will be this value. That means if we look at our kernel approximation, it has error of this magnitude at arbitrary point. And hopefully you remember from the first slide that this has the same form as the predictive variance, of course, for different m's and in a different context. But this is also the error that we obtain if we use a reduced rank approximation, and then we look at the best reduced rank approximation, which was in the previous slide, and look at the metric induced by the RKHS norm. Now, here we also need to look at two more things. One is that what is the average error of this approximation? So if I create, excuse me, if I look at a single point, this is what we get. But if I take an average, with respect to that measure that we have, what would be this average value? And the second question after this we need to ask is, now assume not only we take average with respect to all the points that we have, we also take average with respect to all the design points, all those P points that we have. Now, the first integral here is somehow tractable. The second one is very difficult. And if you look at research literature, just simply because this one is conditional variance, and this one can also be obtained by averaging with respect to the error when you average with respect to the underlying Gaussian process, a stochastic process that we have. There is so much research on this topic. The last one is called the learning curve, how the error changes with respect to the number of points that you have. Of course, here what we are dealing with a little bit different. We are looking at low rank approximation within each region, but the mathematical equations are identical. So here, just to summarize what we have, we use the low rank approximation for each region. We know that low rank approximation has an error, and we are interested in the average error. Now, as I mentioned, the last one will result in intractable integrals. So we need to think of an upper bound for that. And this is the upper bound that we get. So first to mention, to emphasize that our decomposition scheme can be characterized with that function, with the normal vector A. And then we can think of all those equations that I showed as a function of this A. And then we can see that that upper bound for that error will be the summation of eigenvalues, all of them, minus the summation of eigenvalues squared to the square root of square root of that one. And the reason this is important is that this one is in fact just the L2 norm of K. So the first one is just like a trace of a matrix. If you have a unit, that will be the variance. If you have a unit variance, that will be 1. The second one is an L2 norm. So now the good thing is, depending on the distribution that you can get, you can deal with that integration with respect just to the L2, not with respect to the L2 norm, just the value of the L2 norm. So the upper bound can be characterized as a term that is just 1 for unit variance processes. And the second one is just the L2 norm. And then you can seek that vector A, the normal vector, such that that L2 norm of K is maximized. And here there is a constant C that depends on the rate of decay and the number of points, the rate of decay eigenvalues, but I will not talk about this one. I just wanted to give you an intuition to see how we can use that upper bound. So let's forget about Gaussian processes and look at this problem. So hopefully this is clear. This is, let's say, a heat map of a function which is sine of x. So you have two inputs, x and y, but your function doesn't change with respect to y. It only changes with respect to x. So here, dark values is like the heat map of larger values, and this is lower values, and so on. So let's say I am interested in just using parallel hyperplanes, and this is what I propose. Now you see that, and again, forget about Gaussian processes, assume we are going to approximate this function using constant values or piecewise linears with only two lines or two hyperplanes or something like that. So you see in this case, the function in each region is not simpler than the function overall, because if you move in the region on the bottom from left to right, you go up and down the same as if you had not done any decomposition. Now compare it with this one. Sorry. So in this case, if you move from bottom to top, you see the function is simpler in each region. So each of these functions can better be approximated with a limited resource, let's say constant function, compared to the previous case. And we're gonna like extend the same intuition into Gaussian processes. So you can think of that sign of X as something like a Gaussian processes. And in some directions, it changes very rapidly. In some other directions, it does not. And our main theorem is that after obtaining that upper bound, if our Gaussian process has this covariance function, then we need to create subdomains such that our normal vector is parallel to the direction of the largest change. So these diagonal elements that we have here, they characterize how the process changes in different directions. So if they are sorted from largest to smallest, then in the direction D that we have here, the process changes rapidly. That's like the direction X that I showed in the previous slide. So our main result here is that first, that upper bound, the second one is that the upper bound is minimized if you select that A that is proportional to XD. Because of the same intuition, I'm not gonna go through the math because like a limited time, but that's the whole intuition that we have. And the same intuition applies if you calculate that upper minimization. Now, there are a few, I think, good criticism here. First, what if we don't have a covariance function that is like this? As I mentioned, we may have a misspecified covariance function. So there are tricks that you can do. Then you can find just one direction based on something called automated relevance determination using a smaller number of data. So it's important because if we are going to use the whole data, it fits the whole purpose, because our purpose was approximation. And many of these techniques are still of order of n cubed. So that's one thing, but if you just use a smaller subset of data with some degree of accuracy, you can find the fastest direction of change. Another question here is if it's reasonable to minimize the upper bound, because the value that minimizes the upper bound may not necessarily minimizes the error. And that's a valid criticism, but at least based on empirical data, we can say that when we minimize the upper bound, the error improves. And I also wanted to mention just a few points about the application here. So boundary function and control points, that's about how you choose those control points. Generally, you want it to be proportional with the dimension, but you don't want to have a lot of those points. Control point density is also important. The boundary function, you can do a lot of different things. I will introduce a few resources. And hyperparameter learning can be done through, excuse me, just marginal likelihood optimization and gradient descent. And just finally, I just wanted to introduce a few resources here. So the first two are just about local GP. So if you look at the first paper, you can, if you go through it, you can see the idea of decomposition. And then there are a few follow-up papers by the same lead author about different approaches for boundary functions. Some of the results that I mentioned in this talk can be found here. This is with my former PhD student, Babak Farmanish. I should mention that the theoretical results here are a little bit different. There is no notion of eigenanalysis, but I suggest that if you're interested in like the application comparison of this method with other things, you can take a look at this one. And again, here, there are a lot of other things here, like there is the notion of pseudo input likelihood and likelihood approximation within reduced rank approximation, but you can take a look at that mostly for practical considerations. The upper bounds that we developed here are based on these results that you can find in these two papers and the follow-up papers. So this is, as I mentioned, in other settings called learning curve, when you take average values and then look at the average error. And there is like lower bounds, upper bounds, and so on. And upper bounds are usually defined by the techniques that are described in the first paper here. Here is about finite dimensional approximation. But in general, for developing upper bounds, you look at a subspace of what you have, and then you for which the error can be calculated. And then you can say, because my functions are in the larger space, so they cannot be worse than that. And finally, there are two things I wanted to mention here. One is because we talked about average errors and so on, I also wanted to bring this paper to your attention. Roy, who gave the tutorial, is one of the authors here. So if you have time, make sure to take a look at this paper. So this is about two different aspects of Gaussian process that we didn't talk. One is about uniform error bounds, the worst case prediction over a boundary. And the second one is about robustness, once you have specified covariance functions. And there are a lot of interesting theoretical results. And for those who are interested in theoretical results, not only for simple kriging, but also for universal kriging, I suggest that you take a look at this one as well. And that concludes my talk. Thank you for your attention.